Okay, so we started with this problem at a theoretical level. Now we want to solve it at a concrete level and calculate the actual internal dynamics that's required to pinch the key. So let's go ahead and model this with our tools. So let's put the key here in the middle. And note that we have to pinch it with a 45 Newton force on both sides. So we need to get 45 newtons from the thumb. We also need to get 45 newtons from the second digit. So let's start with the thumb. So let's do a drawing of the thumb here and the joints involved. So basically the distal phalanx, the IP joint here, axis. We have the proximal phalanx of the thumb, and then the metacarpal phalangeal joint axis here. So the equal and opposite force acting on the thumb is 45 newtons from the key. That acts at a distance of 1.5 centimeters from the IP or interphalangeal joint axis. And then we have another distance of 3.5 centimeters to the metacarpal phalangeal joint axis, and these are all in centimeters. So we also need to know the moment arms of the different muscles and the forces. So let's include the forces now. So we have flexor pollicis, force in the flexor pollicis longus here. And then we have the force in the flexor pollicis brevis. And then we also have a force coming from the abductor pollicis muscle. And for each one of these muscles, they have a moment arm acting perpendicular to their line of action at each joint. So let's write there. So let's sum the moment arms for each muscle. So we have the flexor pollicis longus, flexor pollicis brevis, and then we have the abductor pollicis, and we have two joints, the IP and the MCP joint. And so let's say that the pollicis, flexor pollicis longus moment arm at the IP joint is 1 centimeter. And let's say its moment arm at the metacarpal phalangeal joint is also 1 centimeter. We also know that the brevis and the abductor pollicis don't have a moment arm at the IP joint, but their IP joints are fairly equal at the MCP joint, so we'll make them 1.5 and 1.5 centimeters. So this is all moment arms and in centimeters. So now we have what we need to solve the equations, so we can start with the IP joint. So at the IP joint, we could say the external moment equals the internal moment. And so then we could start with the external moment. We have 45 newtons pushing into a radial direction that has a moment arm of 1.5. So we can say 45 times 1.5 equals the one muscle that's acting here with the 1 centimeter moment arm. So the force in the flexor pollicis longus times 1. And so this is pretty easy. So this is 67.5 Newton meters, or newtons per centimeter. And so then now we can just keep writing it out, I guess. And so now we want to cancel the centimeters. So we divide both sides by 1 centimeter. 1 centimeter, and that cancels, and that gives us a 67.5 Newton force in the flexor pollicis longus muscle. So now we want to solve this at the MCP joint, and we use our rotary equilibrium equation again, and we can write it all out, but now we have all three muscles and their moment arms, and to balance the external load, and our external load has gotten bigger. So now our external load is 45 newtons times the sum of this distance. So that's 5 centimeters. So we're going to have 45 times 5, and then we're going to include all of these muscles in their moment arms. So we could start with the FPL, flexor pollicis longus, times its moment arm of 1 centimeter here, plus the flexor pollicis brevis, times its moment arm of 1.5 centimeters, and then we have the abductor pollicis times its moment arm of 1.5 centimeters. Now, if we start to solve this, it becomes obvious. We can start here. We have 225 newtons per centimeter. We know that the FPL is 67.5 newtons times 1 centimeter, so that's 67.5 newtons per centimeter. But now what we're going to end, we can't solve for two things at once, so we have to make an assumption about how much recruitment and rate coding we're getting from the muscles. So we'll say that they're going to share the load, and we say that, we can note that I have to give you the answer for one of them. So we'll say the flexor pollicis brevis, the force in the flexor pollicis brevis equals 52.5 newtons, and solve for the abductor pollicis muscle. So then we'll have here, so I have 52.5 newtons times 1.5 plus force in the abductor pollicis times its moment arm. And then we could solve for this, and this will end up equaling 147 or 46.25. So we'll have 225 minus 146.25. Okay, that'll take care of this. And that's is all moved over to the left side. So now all we have to do is divide by 1.5 to get rid of the centimeters. And so what this does is converts all this to newtons and then gives us the answer, which is 52.5 newtons for the force in the abductor pollicis muscle. So we'll just kind of write it out here, equals 52.5 newtons. So then the question is, this is a pretty small muscle, what's its real capacity? So given the PCSA of the abductor pollicis, can it actually produce this much force? So we have some estimates of the PCSA is about 2 centimeters squared. So we can multiply that times muscle stress, okay, which we know is 58 newtons per centimeter squared, and that gives us an estimate of the capacity of the abductor pollicis is somewhere around 116 newtons. So we can see that it easily can produce this amount of force. It's about 50% rate coding and recruitment, plus it also has, we could probably get more output from the flexor pollicis brevis and perhaps some more from the flexor pollicis longus. So the thumb side force production to produce key pinch grip is ample. Let's see if the same situation exists for the second digit. So now we're on the second digit, so we have to kind of do the same process. So we basically have our kind of bone situation is this. So we have the proximal phalanx. Here's the MCP joint axis. And then now we have equal and opposite force acting on the distal end of the proximal phalanx. And the distance from that point of action to the MCP joint axis is about 5 centimeters. So there's our external load, and then internal moment, we have the force in the first dorsal interossei acting to oppose that force. And its moment arm is approximately 1 centimeter. So now we can use our equilibrium equation for the second digit at the MCP joint. So we can say MCP at external moments equal internal moments. So our external is 45 times 5 centimeters. And then our internal moment is going to be the first dorsal interossei times a 1 centimeter moment arm. So we know that 45 times 5 is 225 newtons per centimeter, and then we'll divide both sides by 1 to cancel the centimeters, and then we can get the force in the first dorsal interossei is we need a force of 225 newtons in the first dorsal interossei to create this 45 Newton force we need for pinch grip. So then we could ask the question, well, it's a pretty small muscle. Does it have the capacity to do that given its PCSA? So let's look at its PCSA. So its PCSA is about equal to 3.8 by some estimates. Okay, and what we know is that the stress, so we know muscle stresses can be as high as 58 newtons per centimeter squared. And so this gives us an estimate of about 220 newtons in terms of the capacity of the first dorsal interossei. So it approximates the capacity that's necessary, but it's pretty close. And so some people would use a smaller stress value and would make the point that the lumbricals or other hand intrinsics would need to balance this force. But it's pretty clear that the second digit has a limited capacity to match higher pinch grips as compared to the thumb. And so for this reason, what we'll notice is that when we have ulnar nerve lesions, which knock out all the interossei and the abductor pollicis muscle, that this key pinch grip is significantly impaired.